Welcome back to our Explainer series, Inside Time series. This is episode 3, and man, do we have a cool one for you today. We've already laid down the groundwork for time-dependent data, right? Well, today, we're unlocking one of the absolute earliest, most influential forecasting algorithms ever cooked up. It literally changed the game for how we look at data over time. And it all kicks off with one really simple yet totally profound central mystery. So think back to episode 2 for a second. We looked at moving averages, which are great for smoothing out all that noisy data to find the underlying trends. We were basically just averaging out the past. But what if we stopped doing that? What if instead of smoothing out the past, we actually let those past observations directly predict the future? Seriously, can yesterday's data point mathematically forecast tomorrow's reality? Let's find out. Chapter 1. Learning from the past. To unravel this mystery, we really need to wrap our heads around this idea of temporal memory. Because, the universe doesn't just hit the reset button every morning. Whether we're trying to predict wild swings in the stock market, tomorrow's high temperature, electricity demand at 5 p.m., website traffic, or even insurance claim volumes, yesterday usually holds our best clues. I mean, think about it. If it's 90 degrees out today, there's practically no way it's going to drop to 30 degrees tomorrow. The system has a memory. And that brings us right to the ultimate tool built to capture that exact memory. Enter Auto Regression, or what we usually just call an AR model. This thing is an absolute foundational pillar in time series forecasting. And the name totally gives it away, right? Auto just means self. Regression means predicting a value based on other variables. So we are quite literally regressing a variable against its very own history. We're essentially asking the data to predict itself. Pretty neat, huh? Which leads us to Chapter 2, How Time Remembers. Okay, so how does this actually play out? How does an algorithm literally walk backward in time? Well, it uses what we call a lag. Think of lags like footprints left behind in the sand. Today is our current value, right where we're standing. Yesterday is our first footprint, or lag 1. 2 days ago is lag 2. 3 days ago is lag 3, and you get the picture. In an AR model, these footprints speed forward. The algorithm looks at those past echoes and pieces them together to guess exactly where the next step is going to land. But, and there's always a but, here's the catch. Not every footprint matters equally. We actually have to make a choice about how far back we want our model to look. Take an AR1 model, for instance. It has super short-term memory. It only cares about lag 1, just the immediate previous value. An AR2 model stretches that memory out a bit to include the last 2 previous values. Because let's face it, not every past observation is going to pull its weight in predicting the future. Just like real footprints, the older ones tend to just wash away. So the big takeaway here is that we generalize all of this into what's known as the ARP model. I want you to picture P as an adjustable dial on a soundboard. You can literally just turn this dial to tell the system exactly how much history it needs to hold on to. If you set P to 5, boom, you're using the last 5 observations. Finding that sweet spot for the dial, that's the secret sauce for a perfect forecast. All right, Chapter 3, The Mathematics of Auto Regression. Now that we've got the intuition down, let's peek under the hood and see how this thing actually crunches the numbers. Training an AR model basically boils down to 3 logical steps. First up, we gather our historical observations. Our lags. Second, the model goes into full detective mode. It estimates parameter weights to figure out exactly how much influence each specific past day actually had on the days that followed. And finally, step 3, it calculates the residual error. That's just the difference between what the model thought was going to happen and what actually happened. We can visualize these math components pretty intuitively. First, you've got the intercept. That's just your baseline expectation, like what the value would be if absolutely nothing else was going on. Then we have the coefficients. These are where the real magic happens. Remember that soundboard analogy? Think of coefficients as individual volume knobs for each lag. The algorithm cranks the volume way up on lag 1 if yesterday is a really strong predictor, but it'll mute lag 3 if 3 days ago is just totally irrelevant. And finally, that residual error we mentioned, that's the unexplained noise. It's just the random, messy chaos of real life that historical data can't ever perfectly account for. So you're probably wondering, how do we actually know where to set that p-dial in the first place? Well, we use this nifty statistical tool called the partial autocorrelation function, or PACF for short. Now don't worry, you absolutely do not need to memorize the math here. Just know that a PACF chart is designed to isolate the pure, direct impact of one specific past day on today, completely filtering out all the days in between.
When you're looking at one of these charts, you just find the point where the bars suddenly drop off to zero. That drop-off tells you exactly how many lags are actually worth keeping. It's literally how engineers perfectly tune the memory of their models.
Moving right along to Chapter 4, Engineering Auto Regression. Let's step away from the chalkboard for a second and look at the real world, because the scale of this algorithm's influence is just massive. Autoregression is heavily used in quantitative finance to model things like mean reverting stock prices. Energy grids rely on it to forecast tomorrow's consumption, so they know exactly how much power they need to generate. Retailers are using it to predict their inventory demand. City planners, they're using it to forecast traffic jams. It is insanely fast to compute and really easy to interpret, which is exactly why it's still a bedrock algorithm in modern data science today. But to actually build these systems, there is one massive, absolute rule you cannot break: the stationarity assumption. See, an air model just sort of assumes the rules of the game aren't changing while it's playing. Your data has to have a stable, constant mean and variance over time. If the stock market suddenly craters or some permanent climate shift completely alters average temperatures, your data is no longer stationary. It's a whole new ballgame. That's why engineers will use tools like the augmented Dickey-Fuller test just to verify that stability before they'd ever trust an air model with a real forecast. And that brings us to our final chapter, when autoregression fails. Get ready for a bit of a plot twist here, because for all of its mathematical elegance, the autoregression model has a pretty critical limitation. Honestly, its biggest blind spot is hubris. It just completely assumes that the past holds all the useful information you could ever need to predict the future. It thinks, hey, if we just find the perfect volume knobs for yesterday and the day before, we're golden. But we all know the real world doesn't work like that. Unexpected shocks happen all the time. A machine suddenly breaks down on the assembly line, or a random news event sends the stock market into a tailspin. An AR model is only looking at those past data points, meaning it is often completely, hopelessly blind to these sudden, short-lived anomalies. So we're left staring at this really fascinating question. What happens when yesterday's prediction was just totally wrong? The AR model looks at that error and basically sees a failure. It brushes it off as residual noise and just tries to ignore it. But what if we reframed how we think about this? What if actually that error isn't a failure at all? What if that error is a massive, incredibly valuable hidden signal? Just let that sink in for a second. Sometimes, the biggest clue about tomorrow isn't today's value, it's today's mistake. Think about it. If our model was totally shocked by a random anomaly yesterday, the memory of that shock, the memory of getting it wrong, might be the exact mathematical missing puzzle piece we need to accurately predict tomorrow's correction. And there you have it, folks. We've covered our whole roadmap for today, from learning from the past to how time remembers, the math, the engineering, all the way to the failures of autoregression. But of course, this leaves us hanging with one final provocative question. If errors are actually just as valuable as observations, how on earth do we build a model to capture them? Well, next time we're going to answer exactly that as we dive into moving average models. We'll see how algorithms can actually learn to predict the future by analyzing their own past mistakes. Until then, keep asking questions of your data, and we'll see you in the next explainer.